Hello, everyone. I'm Tiernan Ray with ZDNet, and I'm honored to be hosting this session today on novel AI hardware architectures for graph processing, where we're going to really delve into understanding the new machines that are being built and the new workloads that they are accommodating. We have a wonderful panel today of individuals who've been working at the cutting edge of technology, both for hardware, software, and for systems design, really to run AI and machine learning. We're going to go through a round of introductions. First of all, I'm Tiernan Ray with ZDNet. I've been a reporter covering technology for about 30 years, both covering venture-backed companies and also covering public equity, with a focus on AI and machine learning lately, but I have ranged over those almost 3 decades across a lot of areas of technology, including mobile, database systems, operating systems, development tools, web technology, cloud technology. I think I want to hand it off now to the speakers to give you a little bit of an idea about what they do, and then we can get into our discussion. The session lasts for almost 2 hours today, so I think it'll go by quickly as we have a lot of fascinating things to discuss. So let's see, why don't we start off going alphabetically here. Val Cook, do you want to give us a little bit about?
Certainly. So I'm Val Cook with Blaze Incorporated, and my background is largely non-von Neumann architectures, both hardware and software sides of those. Actually, spent about 25 years of my career in GPU design, as well as focused in media and computer vision implications of that and on the compute side. Also heavily focused on the software side at Blaze and the real applications in this space, and excited to visit with you folks today.
Right. Carlo, do you want to tell us a little bit about yourself?
Yes, hi, I'm Carlo Luschi. I'm responsible for research at GraphCore, and from when I joined the company in 2016, when we just formed a few years back, my goal of myself and the team has been to help the company address this vast space of AI research. This is a fast-moving space which presents lots of opportunity for innovating and for finally find the correct way of cracking computational intelligence. And we've been addressing a broad range of topics, and especially with my team, we've been trying to identify and research types of models which are innovative, that are not necessarily the usual type of using the usual type of computation blocks. And of course, it has been greatly motivating to be part of what is now a fundamental part of AI research, the graph neural networks, that offer, in fact, one of the more promising aspects of innovating in this field.
Okay, Raghu, do you want to tell us a little bit about yourself?
Sure. Yeah, hi everyone. My name is Raghu Prabhakar. I'm part of the team at the beautiful team at Samvanova Systems. My primary background is sort of equal parts computer architecture and compilers, mostly focusing on reconfigurable hardware. So most of what we have been, what I'm interested in, what I'm focused on is, what does it mean when we say data flow, which is really this new paradigm of computing. So it's another flavor of von Neumann architecture. So what does that imply to software? What kinds of optimizations does software have to do? And really, what does that unlock? Because it gives people a new way to think about computing. It unlocks new possibilities which previously were difficult or impossible. So yeah, I mean, excited to be here. Graphs is certainly one of those, all-pervasive. It means different things to different people. So excited to be here, and with the other panelists.
Thank you. Evan, do you want to tell us a little bit about yourself? Evan, you want to take yourself off mute? Great.
Apologies. You'd think that 2 years
I'm going to do that once during
Zoom conferences, I would have figured this out by now. But hi, everyone. I'm Evan Sparks. My background is formerly in my academic life, I did my PhD in distributed systems for large-scale machine learning. I was founder of a company called Determined AI, where we sit above the sort of hardware layer that most of the other panelists here are working on. We make software tools that help machine learning engineers and data scientists explore these novel machine learning model architectures and so on and so forth. And our goal is to abstract away that underlying hardware layer. We want to give people access to that acceleration in the best way possible, and the best acceleration for their task at hand. And so I work with end users in a variety of different industries, everything from autonomous driving to pharmaceutical drug discovery to defense, who are applying these types of techniques to real world problems in their space. Determined AI was acquired by HPE about 6 months ago, where we sit within the high performance computing and AI business unit. And we get to work with a number of different large kind of hardware providers in the space, and we've been able to evaluate many of the systems that are being talked about today. So bring a slightly different view on the problem.
Yeah, thanks. It's great to know that there's high performance compute as an element here. I think we'll get into that. Just to set the stage for you, I wanted to introduce a remark made 2 years ago at the International Solid State Circuits Conference in San Francisco. ISSCC is one of the most prestigious conferences for chip designers. And for the last several years, they've had speakers from AI come to give some perspective to those building chips. So the chip community has been very interested in hearing about what do they need to do to accommodate AI workloads. Last year, 2020, just before the pandemic ensued, there was a talk by Jeff Dean of Google. That was the keynote address. But the year before, in 2019, I was very interested to listen to a talk by Jan LeCun, who is the head of AI for Facebook. And Jan, as you may know, developed about 30 years ago or so, not developed single-handedly, but really popularized and refined and made workable what's called the convolutional neural network, which has been the workhorse of AI to date. CNNs were behind the breakthrough in 2012 by Geoffrey Hinton, University of Toronto, and his students in bringing a dramatically improved level of accuracy by deep learning neural networks on the image recognition competition. And so all of what we have seen in the last 9 years or so, the deep learning revolution coming to popularity, is based on convolutional neural networks, Jan LeCun's discovery, which deal with basically Euclidean data, meaning data from the world that can fit within a matrix or a tensor, can fit within an array, a two-dimensional array. And so most of what has been processed is coming from sensors. It's coming from image sensors from LiDAR, and it's either point clouds or it's images, static images, or it's video. And that makes sense because a lot of our world is very visually focused. We're visually focused creatures, and there's just enormous amounts of this data to process. However, Jan's talk, interestingly, in 2019 was to say all of that may be in the past now. We're moving to a new era, and the era that we're moving to, we will need to look at what are called non-Euclidean data, things that don't easily fit within a matrix. Let me share my screen because I just wanted to give you a little flavor of what Jan told the audience at ISSCC. So I'm going to choose share screen now and click OK and allow. And I'm going to go to this paper. I hope you can see, can the panelists all see this PDF now? Mm-hmm. Great. So Jan, well, among Jan's points were talking about neural networks on graphs. And he said, one of the most exciting recent developments in deep learning is neural networks on graphs. That citation number 50 is actually one of the co-authored papers by Jan and his Facebook AI staff, we'll get to a little later. But I wanted to give you just a gist of it. Many problems are difficult to represent with fixed size tensors or variable length sequences of tensors, but are better represented by graphs whose arcs and nodes are annotated by tensors. This suggests the use of networks of differentiable modules whose inputs and outputs are annotated graphs. The idea goes back to graph transformer networks built to recognize character strings. But recent incarnations of graph neural networks have been applied to 3D meshes, social networks, gene regulation networks, and chemical molecules. Convolution operations, meaning the convolutional neural networks for which really Jan had built his career on, convolution operations can easily be defined on irregular graphs. They're defined as diagonal operators in the eigenspace of the graph Laplacian, which is a generalization of the Fourier transform. We foresee an increase in the usage of such networks for a wide variety of applications which are likely to violate the assumptions of current DL hardware. And there's mention of graph embedding networks, which many of you may be familiar with as well. But I wanted to highlight just that section to give you a sense that although we're focused really now on tensors and arrays in hardware as the way to handle image data, video data, point clouds and such, what Jan was telling the chip world 2 years ago, and it's still true, is that we're moving to a new frontier where knowledge graphs and the many other uses of graph-based information are pushing at what can be handled in computer chips. So down the road, the horizon that we're heading toward, and that all of these individuals already can see, is that what's being processed in AI is coming to, some chunk of it is coming to what people do with knowledge graphs and graph-based information. So with that long-winded introduction, I wanted to open it up to the group first to help us understand. Can you help us understand, first of all, the importance of AI and machine learning workloads today? It seems to be taking up a greater and greater proportion of compute. And for example, Evan, I noted, I think in one of your blog posts for Determined in the last year or so, you had something like there's like a pre-Cambrian and a Cambrian explosion of the size of neural networks such as GPT-3 and such. So is that something you care to give us a sense of what the scope is and the size of AI and ML as a proportion of compute today?
Yeah, absolutely. So, I look at this from a couple of different perspectives, and you can look at the research frontier and sort of the size of the neural networks that are being trained over time, and we're GPT-3 last year already feels like old hat, because now you've got folks like Microsoft and NVIDIA coming out with these 500 billion parameter plus models that are being used for natural language. And if, just to put it in context, a few years ago, a couple 100 million parameters felt crazy. So we're 3 orders of magnitude larger in just about 5 years. And
parameter here is a proxy for greater compute need, right? I mean, you add parameters and things scale sometimes super linearly with the number of parameters.
Right, and but to a first approximation, I'd say linear scaling, but still, whether that's linear or super linear, either way, you're vastly outpacing the speed of Moore's law, for example, which we can get into, and I know that's a hotly contested thing among the hardware crowd, but that's one side of it. The other side of it I look at is practical use of AI kind of in the world. And so you mentioned Jeff Dean earlier. A few years ago, when Google introduced the TPU, they talked about their motivations for introducing, for the first time in their history, a processor that they developed completely in-house, right? And the motivation was they did the story goes something like they did the math on how much they would have to expand their data centers to enable voice search, which was going to be powered by these by neural networks in order to handle that kind of load. And the answer was like, in order to have 1% of our queries be voice search, we're going to have to triple the size of our data center. And that was, okay, that seems like a very expensive way to solve this problem. And so instead, they invested billions of dollars in inventing AI chips, which of course are being used for various other things within Google right now. But the key nugget in that paper to me was that what that tells you about the compute cycles required to do these kinds of applications is that the number of compute cycles at a place like Google now might be over 50% dedicated to AI. That is training and doing inference on AI workloads. And if you think about that compared to the rest of the industry, I would argue that I think the rest of the industry is now at about 1 or 2% kind of its workload is going towards AI. So I think that wave is coming for the rest of the industry very quickly.
Okay, thank you. Does anyone want to jump in and pick up on what Evan's been talking about?
Sure. Well, I can maybe start. And I saw Carlos sort of getting up to say something, so maybe we can.
It's absolutely the same.
Okay. I mean, I don't know if there's anything I would disagree with. I think, but the one additional thing I would probably say is, I think like Evan brought up very nicely, with the evolution of the sizes of the models. There's GPT-3, then there is the Megatron, the Turing Megatron NLG, which is the 530 billion parameter model, and then maybe there's the next one after that. It's kind of giving a nice economics to how much compute you would need, because the structure is not or the structure of these models is in some sense converging. Maybe it's converging to different things across different domains. We will get to that. But it's converging into one of a few models. It's not as big of a model zoo as before. So it's giving a nice way to economize, okay, this is how much compute we have, this is how much it will cost us to build a chip, and so on. The one caveat or one difficulty is this might create a disparity between people who are able to build chips and people who are unable to, or they don't have either the technical wherewithal or the pockets to be able to build chips. So I think one of the issues with this trend is, people might want to have access to AI, but they might not have the technical expertise. So providing easy access or turnkey deployments of these AI solutions, while we hide some of the technical complexity underneath, I think that's probably going to become more important going down the road.
Right. Well, working in the background here is that Google will build anything. And in fact, Evan's former mentor, David Patterson, was conscripted from UC Berkeley to work with Google on the TPU for years. So you had here one of the founding fathers of modern chip architecture was able to be brought in to build the in-house processor. Not everyone can do that. And so the merchant market for silicon and also the cloud services market, which Sambanova is involved in, and GraphCore is involved in this, and the edge devices that Blaze is building, that Val is helping with, will all be important to, I guess, bring resources to everyone else who doesn't build a TPU in-house, is one of the points you're making.
Yeah, that's exactly right.
Carlo, did you want to add something on this?
Yes, I wanted to add something again along the lines of building increasingly large models. Mm-hmm. I think I agree that has been a drive towards larger and larger number of parameters, but at the same time, there have been two other tracks recently of innovation. One is to recognize that computation needs to be made more efficient, and even increasing the number of parameters, having all the parameters doing simultaneously the work and burning more power that as a planet we can afford is not a viable end goal. And then techniques like computational sparsity or selective sparsity, as is thought, is really taking significant traction, having parameters, groups of parameters, so-called experts, that are dedicated and enabled selectively for certain types of inputs. I think it's one solution that finally has the potential of maintaining the task performance, but not necessarily with the brute force of computation has been deployed up to now. And the other aspect that I found interesting, and it's not necessarily having to do with graph networks, that is happening at the same time though, is that until now there have been models for computer vision and different models for language, and then of course the transformer, as I'm sure Raghu was implying before, has been taken over and is now used for both vision and language. But there is this multimodal type of approach that is much more connected to what biological brains do, not have necessarily so many different networks that do all things completely separately, but have a glue of operation, and having one machine that can pre-train and can make use of the significant power consumption of pre-training for then being able to apply to many different modes for them, many different tasks afterwards.
And this was actually recently an announcement by Jeff Dean at Google, which he had been hinting at a year ago at ISSCC.
Absolutely.
Called Pathways. Yeah. And so Pathways is Google's model for a multimodal neural network that can take in image, video, text, endpoint clouds, other
Absolutely.
Sorts.
And it's becoming a broad, sorry for interrupting you, Tiernan, it's becoming a broad trend in current research that I'm particularly interested in, because there have been papers, for example, from other companies as well, that apply this multimodal strategy, and it seems that it's taking lots of traction.
I wanted to take a step back and just help the people who may not be as familiar with what's being developed in silicon these days. Why is it hard to do the workloads that we've been talking about, be they convolutional networks, transformer-based, attention-based networks? Anything in AI and machine learning has launched a renaissance in silicon, of which Samba Nova and GraphCore and Blaze are all terrific examples. We've had GPUs for years. In fact, Jeff Hinton remarked a couple of years ago that, back in 2007 or so, he told all his grad students they should go get an NVIDIA GPU card. And then he called up NVIDIA and said, can I get a free sample? Because I just told 1,000 graduate students to buy NVIDIA cards. And they said, no, we don't give out free samples. So, 1,300% return on NVIDIA stock in the past 5 years means that NVIDIA GPUs have been the state of the art and have made possible the tremendous scale that we've been talking about. But it seems that somewhere within there, there's still room for innovation. And so help us understand, what is it that is difficult to do about machine learning and AI workloads that it can't necessarily be done well by an Intel CPU, an x86 CPU? Anyone want to take a stab at that? Val, you're nodding.
Sure. Let me start that and suggest that you won't find exact agreement in what I'm going to say on the panel here.
Good.
So I think there are a couple of pieces here. One of them is you need to make some fundamental decisions early in what your targets are. And one of those key decisions is whether you're going to provide direct programmability of the device or not, or you're going to abstract that, perhaps not at the levels that Evan's discussing, but even at the ML framework levels or slightly below those levels, that some of the more fixed function types of solutions do, or you're going to provide sort of user customer access to the compute resources of the device. So given that you can make both of those choices and gain significant advantages down either path, Blaze has chosen to go down the direct programmability path. And there are some compelling advantages to that and some disadvantages. Many of the advantages you'll find down the other path, I'll let Carlos and Raghu address. Some of those have to do with pure efficiency of compute, but let me generalize it slightly more. When we look across these types of workloads that we often see in the AI space, we can sort of build three corners. We can talk about sort of capacity limited solutions. We can talk about bandwidth limited solutions, and we can talk about compute limited solutions, and carefully selecting how to cover that space with a given hardware architecture is critical. And it has a lot to do with what kinds of solutions you want to service well. So direct programmability provides a real challenge to throwing sort of one dart and picking the optimal spot or trying to expand that area. And GPUs have put themselves in a position to try to cover all of that space at a tremendous cost. And the cost is typically hardware utilization, die area, and ultimately consumer cost, right? So choosing a path that also follows the programmable branch and provides the sort of expansion and sort of, let me use the term full application acceleration versus AI component acceleration. It has advantages in and of itself, and I think are unique in some ways to edge deployments, where you are fundamentally attempting to provide a semantic compression of a sampled environment in some form, and you need to do that close to the source of that sampled environment. For mechanical reasons, simply getting the data, pulling the wire, whatever the real sort of cost prohibitive solutions, that involved at the edge, and by edge in this case I mean, cameras in large deployments. Think, coliseums or large malls or large public transportations with 30,000 cameras, or in the largest train stations in the world today. Think those kinds of deployments, and in this space the challenges are immense, and that compression is critical, and yet the challenges are often difficult to encapsulate in a finite set of operations, and that's the real trade-off architecturally. So GPUs have attempted to cover that, and they've paid a price for doing that. And many look at that and say, let's narrow the flexibility of the device and increase its efficiency in these three corners. Let me give some airtime to the other gentleman here.
Sure. I want to just make sure that I understand you correctly, Val. When you use the term direct programmability, what does that distinction represent here? What is important?
Sure. So you could argue that CUDA is a data parallel C-like language that allows one to gain access through various auto vectorization, full function parallelization types of compiler techniques to write fairly simple procedural style programs in a way that can be that can utilize highly data parallel, thread parallel type hardware.
Right.
And you aren't limited to sort of the menu of operators in say an Onyx spec or some sort of proprietary API focused on CNNs traditionally or that sort of set. So direct programmability gives you that space and that flexibility at a cost.
And that is the branch, or that is not the branch that Blaze is working in.
So Blaze has chosen to take a unique path down the programmability branch, and without too much sort of company evangelizing, let me just be plain and simple in saying that there are techniques that we feel like we've employed that get efficiencies in the same range as fixed function types of solutions or solutions with a narrowed operational scope. Things like we perform spatial convolutions in dot product style of reduction instructions in the arithmetic pipeline. There's still an ISA involved that we can compile C code directly to that device, and we expose that to the customer. At the same time, you will challenge yourself if you attempt to do that with, say, a multiply accumulate style hardware architecture, especially in the space of rapid context switching and the kinds of things that you need at the edge, where you don't really have the luxury of sort of loading a model up on die and then running that model in batch form all day long. You sort of have to continuously be switching models and adaptively switching models and managing really the complexity of a real world deployment where, classifiers and detectors aren't the end game, right? We need pose estimators and action detection and sort of the full suite of sort of scene understanding and you need to do that in a very rapid, sort of very flexible environment.
So Blaze is working at edge inference types of situations, correct? Raghu,
Yes.
Samanova is working on the training problem, and so is GraphCore. Carlo, I'm interested to help us understand in that context, in the training side of things, what is happening to prompt all these innovations in silicon to handle these kinds of workloads that couldn't be done simply with x86 CPUs, and perhaps they can't be done ideally with GPUs. That's a point of discussion.
I can give a kind of a hardware perspective of the points that Val has just mentioned. Of course, the hardware architecture is the basic, although the software is becoming more and more important, and also we are devoting a great part of our effort to the software stack. But I think we are facing, reconnecting for a second to the point you just made before, that the transformer and other models are becoming more pervasive, and they're certainly providing a great performance, but they're not really computationally efficient. And they map very closely the type of compute that is really easy to run on current hardware, on GPUs and TPUs. So that limits, to me, the possibility of identifying computation that is really more power efficient and also memory and compute efficient in terms of getting the same task performance for the same flops or for the same power consumption. Certainly, big, dense matrix multiplies, which is current today, are not the only way to achieve good task performance, and certainly not the more power efficient way. So in my view, and this was one of our main objectives when we started as a company, to identify what is the flexibility, the type of flexibility that is the best trade-off between delivering a solution that is performant, but doing that efficiently. And yes, and so we have a great opportunity as a community, in my view, because now we are in the transition between what have been done now with these monolithic architectures, machine learning architectures, and what can come next.
Okay, so if I understand you, Carlo, we've shipped millions of GPUs, and we've built these gigantic networks, as Evan was talking about, and that's all been kind of state of the art, but up to now, and it's not necessarily the most efficient compute. In other words, attention-based transformer networks like BERT and GPT-3 are where we're at, but that may not be the best use of compute cycles ultimately for what you want to get.
Yeah, only a second, and then of course I'll leave the time to the other member. So the attention, of course, is a great building block, and there's a lot of conceptual value in that. But in the transformer, of course, and in all the other popular networks, there is this concept of dense big matrix multiplier that is pervasive. And that's where there have been already examples of more efficient architecture that have not been running well on legacy hardware that we've been trying to exploit, that could start to provide with more sparsity, structure sparsity, some other opportunities. But graphs, it's really opening up another level of opportunities, my view.
I want to come back to that in a moment, but I want to give Raghu a chance to talk here from the SambaNova perspective about what has needed to be changed that you're working on to accommodate these new workloads.
Sure. I think both Val and Carlo have given me really good jumping points to sort of address this issue. Start with what Val said, which I like the way Val, you said, we started with the programmability part first, which is direct programmability and so on. I mean that in some sense, in the abstract sense, is the way at SambaNova we have looked at the problem, which is really software first. As we, as this field gets more mature, we'll stick to the just dense machine learning for now. There are these frameworks which are trying to put like a coarse-grained ISA in the minds of people who build networks. And really, the ability of the architecture is just one tiny component. It's how software can exploit it in a manner that's mostly transparent. Or does not have any hand-holding from a team of power users or so on. I think that will dictate the overall efficiency. There's really two parts to it. One is, there's no secret magic in hardware that just gives a transparent boost. You're just making, creating job security for the compiler person, I would say. So you've added these new features. Now the compiler has to now take advantage of these features. Because someone who's building the model does not need to worry about these things. That there's no separation of concerns there. And to Carlo's point, I think if you think about it, as networks get more varied, there's really one or two design points in which people will explore when they're coming up with new networks. And Chris Ray, one of the founders at SambaNova, I think he likes to describe this as product of statistical efficiency and hardware efficiency. So that's kind of the thing that you get. So if you come with a really cool idea, which has really good statistical efficiency, but your hardware utilization is very, very poor, overall, it does not mean that it's a good solution. So people won't go in that direction. And because of this reason, most of the emphasis has been making all these big models look like giant dense matrix multiplies, because hardware efficiency for that is really good. So we're actually leaving a lot of good ideas on the floor because of our programming model that we've all ascribed to. So if we shake up that fundamental thing a little bit, where we go in other directions, new kinds of ISAs. Like Sambhav was all about data flow programming. It gives you another way of saying, hey, it's not just dense matrix multiplies. You can utilize your hardware in another way, and you can get even more performance. And that has ramifications on other things in your architecture. So if you are able to utilize your hardware very well with some other programming paradigm, maybe you don't need the same kind of memory system. And if you don't need the same kind of memory system, maybe you can make better trade-offs with capacity and bandwidth, which will in turn help things like graphs, which have very high memory footprint and so on. So I think just shaking up how software views the architecture and the programming model, it does have ripple effects in all these things.
Evan, did you want to jump in there?
Yeah, I guess I'd like, I think I agree with the points the other panelists have made. I want to come back to the original kind of prompt a little bit here, and I think this knowledge is sort of implicit in the heads of many of the panelists here, or probably all of us, but might not be obvious to the audience, and that is why did NVIDIA become the game in town for these types of neural networks over the last decade? Mm-hmm. And if you go back to Jan LeCun telling his students in 2007 to go buy a GPU card, why was that? Well, if you look at the types of neural networks that Jan had been pioneering for 30 years or so, and the operations that were in those networks, almost all of the compute went to two things. One, convolution. Two, fully connected layers. Fully connected layers are just matrix multiply of big depth matrices. That's, that part's obvious. This convolutions being represented as matrix multiply, that is not maybe as obvious. And it turns out that they can be easily represented there. And for a long time in popular frameworks like TensorFlow or Caffe, before there were these custom kernels written by NVIDIA in cuDNN for convolution that were smarter than just a dumb matrix multiply. That's actually how they were implemented for a long time. And so Jan and his students were looking for hardware that would accelerate those types of operations. And the way NVIDIA architectures were designed at the time were really wide SIMD registers, essentially. And that meant that they were much more suited. There was more die space allocated towards these types of applications than a classical Intel hardware. Because those same operations make for really fast, drawing lots of triangles on the screen if you're trying to accelerate video games, which was really NVIDIA's history to that point. So we found ourselves in this position where all of our networks were, or the popular networks, the ones that were making waves, were using these matrix multiply operations as a fundamental core. And then to Raghu and Carlos' point, suddenly we had this hammer, these NVIDIA chips and others that were really good at matrix multiply, and everything needed to look like a nail for this product of statistical efficiency and hardware efficiency to work out in our favor. And so the networks, the earliest graph convolutional neural network papers actually say, let's represent the graph as a dense matrix and apply these convolutions to it in the same way. The first experimental papers that actually do it. That's clearly an inefficient representation of sparse objects like this, but it was the easiest way to apply that hammer of matrix multiply to the nail of the problem that we're trying to solve. And so what I'm excited about when I look at novel hardware architecture is what are the fundamental core kind of primitives that can be exposed by those architectures that enable me to represent that, say, graph convolution problem or something like that much more efficiently on a hardware level than let's just turn it into a big matrix multiply.
I like it. Yeah, Val?
I have and you can debate the dates here a little bit, but I have an interesting slide you might find interesting for the group. It's really set up from the point of view of a timeline. Let me see if I can. Let's see. So if you look at across this timeline,
right,
the top of the timeline or sort of hardware architectures. And the bottom of the timeline are sort of programming models, if you will. And to sort of reinforce the comment that was just made, we've at Blaze, we call it graph streaming. At Dominova, they call it data flow, and I'm not sure, Carlos, you'll have to help me at GraphCore, but we all are espousing this concept of fundamentally taking a programming model that is now well established in terms of sort of graph-based semantics at the top software level, and mapping that onto hardware that has dedicated capabilities to do things like retain data locally on the device and communicate locally between the compute resources on the device. And many of the things that are just very challenging for GPUs today. And I guess the point of this slide is, if you kind of stand back and squint, I would suggest that the timelines at which non-von Neumann style architectures have been most influential in our past half century or so have been when the software models have lined up with those hardware architectural innovations. And whether they're influenced by the hardware vendors or the software vendors, the point is that when there's a strong alignment conceptually at the software level, that people are willing to think and able to think in solving problems in certain ways, and then the hardware supports that, then you get these strong inflection points where there are just really rich jumps in what happens in our compute space and the problems that we solve and the benefit that we bring to sort of humankind, I guess, to step way out. I don't know if you'd completely agree with that, gentlemen. And let me clarify one thing for Raghu. These data flow machines are the data flow machines of that time era. Today, we talk about a much richer style data flow. So let me not convolute those two words.
Let me just make sure that we understand when we talk about data flow now, we're talking about basically the entire approach has moved to one where, as I understand it, the graph nodes are the operations. They could be kernels. There's some kind of operation that happens, and the flow are the data that flow through those operations. So TensorFlow will produce a graph of compute that is a bunch of operations through which the data, say matrices or tensors, are supposed to flow. And a lot of, so far, what it sounds like been doing in hardware is to try and match that with things like coarse-grained reconfigurable architectures where we can arrange a bunch of compute cores to be those sort of operations, be they matrix multiplies or whatever, through which the data flows. Is that kind of where we've been so far with data flow in hardware, in silicon?
I would certainly concur. I think Raghu and Carlos.
Yeah, Raghu?
Yes, our view, our approach has been the one of taking the abstract computation graph that, for example, is produced by TensorFlow or PyTorch, a conventional framework, and to take it in our software and break it down in even more fragmented elements. And then we associate in our chip. I don't want now to go too much into details of the GraphCore IPU, but in terms of the philosophy of the approach, we have fragmented the compute on a single chip and on the classes of chip into as many possible individual processor cores with their own allocated memory, so that we can distribute all the elements of the computation graph and spread and distribute it over all those elements. So that ties with this description, I believe.
Raghu, did you want to add anything?
Yeah, I think I would agree. I think the way you described it earlier, which is the CG arrays, you have compute and memory elements at a high level. I think that makes sense. I think really the complexity is, I guess when you think about a traditional architecture, we were thinking about the efficiency in terms of IPC, and various other standardized metrics for throughput. How many instructions can you churn through, and so on. That starts losing some meaning when we talk about things like CG arrays. So really, we'll come down to other kinds of ratios that start mattering a lot more. Saying, I mean, it's one thing to have reconfigurable, compute elements, but really, what is the thing that's feeding it? It's the memory system, the communication, and the off-chip memory system. And there's really there's a slider bar here, like a variation of, you can design them to be as fine-grained as you'd like and as coarse-grained as you'd like. And depending on where you park your design, there is this trade-off between your peak and the flexibility. The smaller you go, of course, the more flexible it gets. But the more coarser-grained you go, the more efficiency you get, because you can pack more dense units. But the unhappy medium, I suppose, for everyone is I guess, the more tricky business here.
Carlo,
if I may interject very briefly, Raghu, I agree with your concept. In my view, and of course that's a philosophy we have embraced, the efficiency of the hardware for a certain target level of fine-grained objective is given by the amount of parallelism that the hardware provides. Having the possibility of doing at the same time many individual processor elements of processing, hopefully on a single chip. Hopefully you can still be able to be efficient in terms of running enough operations, but at the same time giving you the possibility of doing different things, the multiple instruction, multiple data paradigm, or doing different things on individual large set of programs that run at the same time.
Yeah, that's actually a very good point. Go ahead, Tina.
No, go ahead, Raghu.
Yeah. I mean, that's actually a good point. It's a good observation. I think the many instruction, multiple data, not sticking strictly to SIMD, I suppose, is where you were going, or SIMT.
Yeah.
Because it does unlock this other dimension of parallelism. Like you're not tethered to the ground on finding big data to do exactly the same operation. For example, with Dataflow, you can do coarse-grained pipeline parallelism. You can have a coarse-grained pipeline at the batch level, another pipeline at the lower level. So when you do things like standard compiler transformations like tiling, it enables better data locality to use,
Yes.
and because of this MIMD, you're able to keep all the units busy without just SIMD.
I want to come back to Evan's point, because it's an interesting one, because there is a lot of achievement of parallelism of various sorts, but Evan was getting back to a key point, which is a data scientist wants to do certain things and looks sometimes to hardware to what's going to be made possible. And actually, this was a point Jan made to ISSCC, talking to all these chip architects, that ultimately what we can do is defined by what you build. Meaning what we can build as a neural network is defined to an extent by what you build. And I think we've all been saying, starting in sometime in the early noughts, we had a discovery of GPUs as a great way to build neural nets using matrices and tensors, vector-based processing, but that we've there's a sense that only goes so far. And I wanted to offer, again, something that Jan had said back in 2019. He said a tensor core, for example, which is the term for how a GPU, an NVIDIA A100 GPU, handles training of data. He said a tensor core is basically optimized to do lots and lots of 4x4 matrix multiplications. Right? Now, so if you can, reduce all your neural nets to 4x4 matrix multiplication, you're okay. But it's maybe not an optimal way to run multiple convolutions. So already there's a sense convolutional neural networks bump up against the limitations of the device. And to go even further with that, I wanted to share a quote from Jan on the screen, really talking about where he sees the problem going from here. This was, again, Jan, an interview, and I said to him, so your talk said matrices and tensors. I think everyone, panelists, can you see this document?
Yes.
Okay. Matrices and tensors go bye-bye. So what takes over if it's the manifold or if it's the graph? Meaning, the data that you're dealing with is in a mathematical manifold, or it's a graph structure of data, like a knowledge graph, what does that look like as a fundamental compute unit in something that's both broad enough to have lots of workloads, it can be a viable problem to tackle in volume, but it's specific enough to the problem to be efficient? Do we know? And Jan's response was, yeah, that's a good question. I don't know, actually. I think, the real hardware geniuses will have to invent new ways to do those things. I mean, to some extent, you can think of this as a similar set of operations as we currently do in neural nets, except that the way you access the data is through interaction. So instead of things coming to you in a neat array, what you have is an array of pointers. Then you have to fetch the data, that is pointed at by this. That's what a graph is, really. So my takeaway from that is Jan was saying we need to break outside of the matrix structures we're using. We need to break outside this conformity to tensors, and we need to start to look more carefully at what is the graph of compute telling us, and what is the data flow telling us about that. And to Evan's point, something about how this is done in compilers and in hardware is going to inform how neural networks, I guess, are going to be built beyond today. Does that make sense, the way that I'm interpreting that?
Blaze has a little bit of a unique perspective on that one. I'll just comment briefly, and
Please,
then
yeah.
So because we've both espoused direct programmability and sort of AI transforms from the ML frameworks, we run into highly varied input data, everything from point cloud data to highly unstructured pointer type, structures, and historically GPUs have spent a substantial amount of their die area and their power budgets on sort of scatter gather logic, right? The ability to bring unstructured, if you will, information, pack it into some dense SIMD style vector, process that, and then scatter that back out to memory again. And those architectural choices at the die level, how much of those resources do we invest in efficient access to, let's say, less or unstructured data, do you provide? And it's a serious trade-off in terms of resources, especially when you talk about bandwidth and efficiency in the memory itself. And the answers, back to Carlos' point, the answers aren't easy. And Raghu mentioned there's not magic. It's really about trying to look far enough ahead and not too far ahead that you can pick those right design points to effectively influence the software algorithms that will come into fruition in the future. And in reality, that does happen. We've said that in several different ways. Evan kind of points it out very plainly with the dense matrix example, but it happens across the board that the innovation in software is in sometimes heavily and sometimes less so influenced by that available hardware. And I perceive that this ability to access less structured data will become an increasing piece of the die area and the power budget in the future.
Where less structured in this case refers to not necessarily one big tensor.
Right.
Or matrix multiply. It's coming in other ways, maybe, as Jan suggested.
Yeah. At Blaze, we accelerated, complex sensor fusion with point cloud and image-based data, and merging those things together is not a trivial task in the form of trying to map that all into just simple tensors, right?
Did anyone want to add to that, Raghu? Yeah.
Yeah, I think I would agree with that. I think the other thing, which I guess is along the lines of what Val was saying with this different types of data that's present in an application. We've seen something very similar. It's not exactly graphs per se, but we've certainly seen models from or potential models from various use cases where you're seeing a mixture of dense and sparse computation. So it does sound like, it's dense matrix and sparse matrix multiply, but they have completely different execution profiles. And if that's how the world is going to be in the future, I'm not going to try to wager and predict anything here, but if we envision that just because we have disparate sources of data and different data has different characteristics, if we imagine that the future is going to be a mixture, some data will be dense, some will be sparse, and we have to deal with the mixture. I think the thing it puts pressure on is, I keep coming back to the memory system, because it's still memory at the end of the day. We still need to feed the beast. If it's sparse, you don't have as much operation intensity, but you do have all these both on-chip and off-chip scatter-gather operations. And not just that, you need to have a system that is able to sustain a lot of outstanding memory requests, because you need a lot of address bandwidth. You need to keep the whole pipeline full, because you're issuing so many requests. So I think of course, none of this comes for free. But the good thing about, I guess, architecture is like you design it based on benchmarks that you think is going to be representative for the timeline, or at least you use them as guides. There's always an academic worst case for any architecture. I think that's what it's like the old textbook philosophy. So I think having similar to what TensorFlow and others did for like dense ML, having some sort of a representation, having some clarity around exactly what kinds of sparse, how exactly is this entering into the workspace. I think that's going to add a little more clarity on what aspects of the architecture needs to be revisited.
Mm-hmm.
Is that would be my take on it.
Anyone want to add to? Carlo?
Sorry.
Yeah.
No, I think absolutely. I totally agree, and I think that is an opportunity, because again, there is a big overlap with the point I was mentioning before. If the hardware architecture provide opportunities for fine-grained computation, those are the difficult aspect to me. And if those opportunities are supported, then of course, for any hardware, it's relatively easier to accommodate a larger matrix multiply than it is to fragmented computation. So once at that point, the software can get in and try to orchestrate the mixture of the two types of operation, which are the foundation of, for example, graph neural networks that have the sparse access for aggregating the neighborhoods of each individual nodes, and then the neural networks that have the usual fully connected layers with dense computation. So these two things can be easily orchestrated by the software, in my view, if the hardware support the fine-grained compute. And the other aspect that is crucial that you also mentioned, Raghu, I totally agree, is how the memory is deployed. Especially with these graphs becoming larger and larger, in my view, there is the need of low-cost, massive off-chip memory where to store the graph. Now, at that point, it's a bandwidth issue, because, of course, all the modern AI workloads are pre-compiled. The software compiles both communication and compute. So the latency is kind of taken care of to a certain point by this way of approaching, but the bandwidth is still an issue. So bandwidth to a massive external memory is the issue. And for me, for our philosophy, the way to tackle that is to have a large amount of on-chip memory. So then you can access all the data that you need without reducing your computation speed, you do the throughput on chip. And then, of course, the software again can orchestrate phased execution of loading or streaming data as it is needed on the on-chip memory according to the computation graph. But yeah, it's a fine balance between the two aspects that Raghu pointed out, the fine-grained compute and the dense compute. But I think if the fine-grained compute is supported, I think the software will have the opportunity to make it glue together and to make it work effectively.
Okay, and I would think that already with these new kinds of accelerators, both on the training side for GraphCore and for Samano, and on the inference side for Blaze, it seems like we are at that stage where we have fine-grained compute choices supported. So we've kind of solved that problem, I would think. correct or no?
And it's only a question now to go there and to try to discover new ways of having more effective graph neural networks to tackle even further.
Well, let me ask you this. Let's turn it back around to it's 2007. People suddenly discover they can do a lot of very large matrix tensor operations with a GPU. Are there things in hardware now that I, as someone who wants to work on graph-based data, need to immediately grab hold of, either at a low level, if I can do that, or through frameworks or through compilers like the Apache TVM, right, is a compiler technology. And Evan's work, Determined AI's work, is a middle layer, kind of to stage workloads in various ways. Are there things in these new accelerators that I could start building for as a neural network developer that would immediately change what I'm building tomorrow from what has been my focus on thinking about everything as large tensor operations or matrix multiplies? Val?
Let me give you one interesting one. I'll stay hypothetical here. We talk about data scatter gather. There is, in fact, of course, control scatter gather as well. And in spaces where you have highly dynamic workloads, where you want to control how that compute resource is allocated, is in fact a little bigger problem than just addressing sparsity or even unstructured data and sort of packing that in. When you start to suggest that I now want to operate on sort of less structured data and I want to apply my compute resources sparsely, I want to do things like, say, I want to apply these resources dynamically in this area and not in this area, and you start to have, for example, Blaze espouses a thread spawn thread semantic, where you can allow a given unit of work to fracture its work into multiple threads, or to aggregate its work into single threads from multiple threads. And you begin to provide language semantics that fundamentally don't exist well today in any kind of fine-grained fashion. They kind of exist at very high level semantics. You can enable much more dynamic models, and it's something that can catch up, that can make a difference.
Mm-hmm. Okay. Evan?
Yeah, sorry, I keep coming back to the memory system again, which is, and even I think with dynamic control is actually a very good point. I think it's in some sense CPUs have spoiled us. We take control for granted. Every time we move to something that's slightly distributed data flow, the programming model, it exposes control to the programming model in a slightly different way. I mean, dynamic control is a good point, but from a memory system point of view, certainly scatter gather is important, but that addresses one aspect of these kinds of operations, which is indirect accesses. Doing A of B of I, or A of B of C of I. These indirect accesses. If there's a way to keep them pipelined, both on chip and off chip, with sufficiently sized memory capacity, to Carlos' point, that addresses one aspect of the problem. The other aspect is dealing with these data structures that fundamentally aren't dense matrices. So I would probably postulate and even say that if you're doing A of B of I, it's sure you're doing an indirect access, but in some sense you can understand what's going on here. When you're dealing with a data structure like a set, for example, where you need to check for occupancy very quickly, and these data structures are fundamental when you're dealing with graph algorithms.
Yeah.
There, it's not, especially when you build something that's not inherently sequential, you can quickly lose performance. So I think having support in that direction, where the set operations can be handled efficiently, or at least with minimal enough lift to software that they can build abstractions on top of it. I think I probably put that up there in this list.
You're talking about not inherently sequential. You're talking about dependencies that should be clear from the compute graph, meaning the compiler has prepared, staged what needs to happen. And so some of those things are going to happen out of order, but presumably smart compiler software like what SambaNova has, what GraphCore has with Poplar, these have solved these kinds of issues, or you're saying this is an outstanding problem, Raghu?
So the problem, I guess I was referring to a slightly different problem, which is the out of order or the sequential nature. These are operations where it's very difficult to extract parallelism. So in some sense, they're irregular, which is where the dynamic control argument goes. It's not very clear. If you use n number of functional units, you will always get a speed up of n. It really depends on how many conflicts there are. So there's certainly those kinds of workloads which are sequential or which are irregular. Having some sort of support which enables software to write these speculatively parallel programs, I think they are important.
Evan, did you want to say something before?
Yeah, I mean, I think sort of back to your question of to rephrase your question, you kind of asked, are there existing hardware primitives that I, as a machine learning engineer, or should be aware of that already exist in silicon today that I could use potentially to accelerate my algorithms that aren't just matrix multiply, right? That's one question. I'm not going to address that question, actually. I'm going to address a slightly different question, which is, as a hardware designer, what are the algorithms and access patterns I should be aware of as I'm designing my hardware that represent sort of the next wave of applications that I might have to support? And I think, when I'm thinking about this question, something that I go back to is, what about the machine learning that we all used to do 10, 15 years ago before deep neural networks were all the rage, right? And I'm thinking like big sparse logistic regression models, or tree-based models, XGBoost and random forests and so on, or let's say things that were powered by Gibbs sampling in the graphical models kind of view of the world. A few years ago, Pedro Domingos, University of Washington, wrote this great book that is sort of a very digestible kind of, I'd call it pop sci book, that's sort of a history of machine learning. And in it, he breaks down the history of machine learning into 5 kind of camps. And the camp that is like sort of winning today is what he called the connectionists, the people who focused on neural networks and whatever. But there were all these other camps, people who were really focused on optimization and kernels and support vector machines and so on. There were and I won't list all 5 camps. I do recommend everybody who's got an interest in this stuff read the book. But I think that each of these camps probably has a couple of primitives that they really need to support in order to do their machine learning very effectively. And if I'm thinking about new horizons for hardware support for machine learning, it's probably not going to come from something that is absolutely net new, a brand new idea that nobody's had before. It's probably going to come from, hey, what if I rephrase this old idea through the lens of, I have all this data now, or I can combine it with neural nets in an innovative way. And to the point of Raghu and Carlo, mix that kind of sparse access pattern with the dense multiplies in some new way. I think that's where we're going to see a lot of innovation kind of come from.
I agree, and that's a great point. And in fact, there's always been a great motivation of our work, the fact that we are intimately convinced that in AI in general, not only in graph neural network and graph processing, we are in the middle of a path. We are not arrived yet. We are still in the process of discovering what is the best way of doing artificial intelligence. So every hardware platform, in our view, needs to have needs to give the possibility to the researchers and the developers to try new things, to try new approaches, to experiment, and then So we cannot force ourselves in a box of let's do this efficiently, because things will already be moved in a couple of years, but we need to move the field ourselves.
Roger, you want to add?
No, I was going to say that's a great point. I think just empowering people who are in some sense projecting into the future. They're the best people who can predict it because they're inventing it.
Yeah,
we can project as much as we want, but really it's if they have the power to try new things, I would in some sense argue that that's probably what led to the success of NVIDIA, because CUDA was a really powerful tool. And you know, they were ready for it when the deep learning wave hit. So I think that the providing the right tools for people who are performing these explorations, and enabling them to think in these new educating these new programming paradigms, I think they hold key.
That's fundamental in terms of also. Sorry.
I'm sorry. Go ahead, Carlo.
No, sorry. I'll be brief. I totally agree. It's fundamental, like Rago said, that we provide the software, not only the hardware, for experimentation, right? But ultimately, I believe the possibility of doing different computes efficiently is eventually enabled by the software down to the hardware architecture.
And to Evan's point, looking at all the things that have been floating around is one vector of investigation. The comment by Jan suggests, and to the point of of some element of this webinar, we want to do graphs. We want to treat non-Euclidean information. So we want to move beyond just convolutions on images and video and point clouds. So what is hard about doing graph data that comes into the machine that is input in the form of a graph? What's hard about doing that in general? Can you say?
Well, I can take a stab and at a high level, and then hopefully what I'm going to say is not going to be too controversial, and then I'm sure we can.
Hopefully it will be, actually.
Hopefully it will be. All right, I see. Well, I mean, I think the number one, leaving out GNNs for now. I don't know if it's
graph neural
network changes that, but yeah, leaving out graph neural networks just for the minute. If you think of any conventional graph algorithm, one stark difference between that and even take a classical ML operation is that the ops per byte is very, very low. Like the actual compute you're doing is not as important as the order in which you traverse the node, from where you are getting your inputs from. So it becomes very, very memory dominated. So all the conventional notion of this can do those many teraflops, etc. Probably not the first, the most important metric for graphs. Second thing is, we already talked about scatter and gather, but for sure that becomes a first order constraint. Like access patterns are dynamic. You'll have pointer chasing, you'll have gathers and scatters with dynamic lengths. And third, it does have high memory capacity requirements as well. The graphs tend to be huge. They come in various formats. Depending on that, the impact on the kernel that you're trying to build, or the operation is going to be different. So when you're dealing with architectures which have very small memory, and there's always a trade-off between capacity and bandwidth here. So when we're dealing with architectures that have access to a small amount of off-chip memory, it quickly starts restricting you. So it forces you to either scale out or bite some level of complexity quite early on in the game. One of the research that we were doing as part of when I was in grad school was we were frequently, this is at Stanford, and we frequently found that for these large scale graph algorithms, like in things like triangle counting, Jacquard similarity, and things like that, it's huge. When you do it on bigger graphs, you can quite often beat the GPU by on a CPU, because you run into capacity issues very quickly. So I think the exactly how you design the memory system, it's not an immediate slam dunk to have something that has high bandwidth because it comes with lower capacity restrictions. So I think that parking the design point at the right place is really the hard thing. And okay, I'm going to stop talking now. Just comment.
Oh, if I can, I don't.
Please.
Kernan, if I can add to Raghu, I totally agree. That's exactly, absolutely also my view. Graphs are really the place where we deal, at least the way they are done today, with both fragmented access to memory and fragmented compute, and still also dense compute. Not as much as in the transformer, but still the neural networks that approximate the message function of the update function are still conventional neural networks. And so the two issues there, along the lines that you just mentioned, I agree, are the memory. We need the large amount of memory for these very large graphs. That are the ones that is the direction where we are getting at. At the same time, we have the bandwidth problem, the problem of accessing in a fragmented way the memory. So the arithmetic intensity, it's typically significantly reduced, and that's of course I agree that some things can run faster on CPU than GPU, but then our goal is to make them run both of them fast. In that case, the CPU is faster, but they're both very slow, I suppose. Otherwise, yeah, that's a challenge.
So despite the fact that we have a lot of innovation at this point, are we still trying to solve that kind of memory and bandwidth issue for
Yeah,
hand?
I mean, no, absolutely.
I would actually go a little bit of a different direction and say that I think to Raghu's point, these are almost a property of the computation at hand rather than necessarily a problem. Like, I don't know if it's a problem that we should be solving directly in chip design, or whether we should be thinking about it from a more holistic perspective of how do you design the overall system that is designed to solve these problems. So, for, let's say, the triangle counting example, just to have one, that might require
the triangle counting example.
Sorry, triangle counting is like a common graph analytics operation where you're looking for communities within, say, a much larger graph. So if you think of a graph like Twitter social network, and you want to find the people who follow each other in a triangle and use that to build out a sense of what are the cliques or whatever in this community.
Okay.
That's an operation you might want to perform. Turns out that primitive doesn't require, to Raghu's point, a ton of high frequency computation. Instead, it requires you to loop over that big list of edges that you have between every follower in a Twitter network over and over again through some iterative process. And that's an incredibly memory intensive operation. If you can fit the entire Twitter adjacency matrix, or adjacency graph, I should say, in memory, do that. If you can't, you got to get clever about how you swap these things out and maintain lookup tables and whatever. And so if that's the problem you're trying to solve, you might come up with a very different system and a very different set of hardware requirements than if you're trying to say train a deep learning model with convolutions in the middle of it.
Yeah. Go ahead, Carlo.
Sorry, because I realized that I left one bit pending from my previous point, which of course was very correctly made by Evan. I totally agree. The solution to the two problems I was putting forward, the boundary problem, the memory problem, is a system issue. Is a system solution, and of course our view is that our way to try to, of course, is our current work, but the way we are trying to solve those problems is to have a very large amount of low-cost external memory, DRAM, and a very high on-chip memory that reduces the bandwidth probably to accessing the data that is on chip. But of course, there might be other ways going forward for augmenting this, supported by software.
Val, does it look the same from the inference standpoint when you make predictions? How does handling graph-based data coming into the machine look when you're making predictions at the edge?
Let me be open. I think the other gentlemen have a lot more experience than we do. We're primarily still seeing the embeddings is the technique for sparsity and discrete data being, packed back into tensors. And that's fundamentally what we have most of our experience with. So I can't address it honestly with experience. Let me speculate just a little bit, is that it really is this, I like to think of again as that triangle of optimization points. And Evan suggests that different problems, you can pick a different spot in that triangle and build silicon around that spot. And it's if you want to pick the dead center of that, you'll have the greatest flexibility and probably the least efficiency, right? And so it's a constant trade-off of where you choose to be and where you think we will be in the future, working with innovators in this space. And so it's very challenging. I would suggest maybe one other thing we're going to conflate words again, and I struggled, but data flow graphs or task graphs or streaming graphs, this is about describing both the data movement and the computational work to be done, has a rich semantic value to it. I like to kind of say it in simple terms is suddenly the hardware can see the future, right? We can see not just the current task or hundreds or thousands of instances of the current task, but now we can see many tasks, and we can see the data that's moving between those tasks. And we can do very simple things that make tremendous difference, like prefetch constant data. We can pre-allocate space in on-chip resources, to Carlos's point. There are just so many things that we can do when you've got larger vision of the work to be done than sort of, here's your next instruction in a von Neumann architecture, right? And so in that world, if there were a way to then take this definition of graph that's about efficiently describing work to be done, and we could in some way map that onto knowledge graphs, or we were approached by a national lab that's very excited about action graphs, where there is a shift in the compute ratio to navigation ratio in graph traversal, and those kinds of things, where we can start to map both, if you will, the topology of the data and its relationships with the topology of the compute to be done. And suddenly, and I don't have answers here, but suddenly it feels like there's an intuitive net win here, right?
It feels like it. Yeah, it feels like the domain and the problems start to mesh with the innovations in hardware and software, and how it, as you say, sees the total workload, the total problem. So how do we do that? Any takers? I wonder if the problem is ultimately in what you're saying, Val, where these things meet up is in software at a compiler level, in how you take what you want to solve with graph data and you give it to what you have that, as Raghu says, Carlos says, solves the maybe as it does work at HPE with staging, parallelism in a system level, these things start to come together. Evan,
Sorry. Jumped on mute and off it again. So what we see in at kind of the at the scale that we're dealing with is problems where the compute doesn't fit on one GPU anymore, and this could be because you've got a big language model that has these hundreds of billions of parameters, or it could be because, using a single GPU or even 8 GPUs in a single machine is based on the size and complexity of the model you're dealing with. It's going to take weeks for your job to kind of finish training and converge. And so what we do is and forgive me, I'm just a dumb systems guy. I say, like, throw more power at it. The old Tim Taylor from Home Improvement, if anybody remembers that show from the 90s. I'm dating myself, I guess. But so we say, okay, how do we throw more GPUs at this problem, or more accelerators generally at this problem? And we start looking at different ways to parallelize the training of these models across multiple GPUs. And there's data parallel techniques, there's model parallel techniques, there's pipeline parallel techniques at a level beyond what can physically exist on one die of silicon. Of course, these same techniques are being used under the covers on us and by our compilers that are targeting a single chip. But at some level, at some point, you kind of have to say, okay, we're going to break out above that. And so then you ask the question about, what is the level of abstraction that I need to offer my end user, and what are the core primitives that I want them thinking about when they're designing these jobs that are going to run across multiple kind of machines? And it determined in HPE and determined more specifically, we've taken a view that really we shouldn't make these concerns about how you parallelize things and so on a problem for the end user. Instead, the framework, whether it's TensorFlow or PyTorch or whatever, should be offering primitives that let you express kind of declaratively, this is the network I want to train on this data, and then the system should be able to go figure out the access patterns, how it wants to do coordination among multiple GPUs, the style of optimization it wants to do, and parallelism it wants to take advantage of. We didn't invent this idea. This is, I'm a databases student at heart, and so in databases you have this idea of a declarative query that you issue to a database system, a SQL query that says select star from whatever, roll up by however much, and the system goes and figures out how to parallelize across multiple machines if that's how the data reside. We think a very similar kind of paradigm should exist for these types of jobs, and so when I'm thinking about the software design side of things and scale and adhere and supporting these types of workloads, the question for me is really, like, always, where should we draw those abstraction boundaries? We want to offer direct programmability to the really advanced users who, like, absolutely need it and are going to get in the weeds and worry about message passing and so on. But at the same time, for 90% of use cases, we think you should be able to offer a kind of, here's my model, go train it, sort of approach to things. And then from my perspective, it's like, okay, now my team can get in the weeds of selecting the best all reduce operation for a particular model operation and so on. So I don't know what that means for hardware design, other than the more you can accelerate those operations, the better, and that might be direct access.
Carl is going to tell you what it means for.
No, I think, because I totally agree with the goal. This is really the goal that every software stack should deliver. Should deliver to the user input what the end goal is, what the implementation requires, and the software sorts everything out. But then I really wanted to add something here, because we make the point before about the original matrix multiply of GPU, and there is this other aspect that has a relation on what we can do for distributed processing as well. That the GPU is not only the GPU and TPU and all conventional hardware. Legacy hardware is not only particularly good at matrix multiplies, but need many exactly similar types of matrix multiply, single instruction multiple data again, to be run in parallel, which is the other side, the even more dangerous side of conventional compute. Because if we drive this paradigm towards how do we do distributed training nowadays, every company with data parallelism or pipeline parallelism, the only way to maintain hardware efficiency and speeding things up is to increase the batch size for different replicas, distributing data over different replicas of the model or different pipeline stages of the model. And then in both cases, the batch size increases linearly with the number of replicas and number of pipeline stages, which again is not ideal, because not only is power inefficient and computation efficient, but also goes again the statistical efficiency of learning of SGD and all the optimization algorithms that don't need the large batch size. They have at some point a detrimental effect on task performance simply because the batch size is too large. So of course, even with full agreement, I started from what the software should provide to the end user, but then the hardware should really provide alternative ways of doing parallelism, not only on chip in terms of architecture, but in a way to devise distributed processing over a large number of chips with respect to what we can do today.
Yeah, and it seems that goes back to Val's point, Carlo, about dependencies and understanding the larger picture. If this is your point, you're not just working from the latest instruction in registers. You're trying to understand how does this problem unfold in time and space, and then how does that appropriately map to what you have. Raghu, did you want to say something?
No, I think the points from the panelists are really well taken. And from my point of view, it's like, I think we've talked about this earlier. Going back to your first question of, okay, how do we solve this problem? There's this crossroads of hardware innovation meets new, techniques with GNNs. Really, it comes down to, again, enabling people. Because in some sense, we are going down the same path of dense neural networks in the evolution of what we are exploring. I was listening to a lecture from Yuri Leskovich from Stanford, and he's talking about graph sage and a few other training techniques. And Evan brought this up as well. The seed for innovation has been, oh, this doesn't fit on my GPU, or the utilization for the GPU is not good enough. So how do I change the algorithm such that we can work with the constraints? And the constraints happens to come from the GPU, because that's what's available. That's what people understand very well. Now, if we say, okay, you know what, let's say that that's not a constraint anymore. Let's say your utilization can be higher. This is exactly what Carlos was saying. Was saying, and we have a different way of managing data on chip. Programmer managed scratch pads, data flow communication, large amount of on-chip memory, large amount of off-chip memory. Now there's a completely different design space where some of the existing pruning techniques might not matter as much. I mean, you might have to do other things, but in some sense, it's a superset over what has been explored. So I think in some sense, and giving the right tools, it's like, I'm in California, so I'm like, I try to make the analogy of the gold rush, and the person who made a lot of money is the person selling the shovels. So empowering people with the right tools that people can explore, saying this is actually possible in these kinds of architectures at a reasonable training time. I think that's going to spark research in areas which we haven't seen so far.
NVIDIA has sold a lot of shovels, obviously. But I want to offer one thought, which is, as far as I understand, TensorFlow as a framework focuses the work around tensors, as it sounds. And it seems like, if I'm not mistaken, that had an influence on NVIDIA in the past several years, meaning that about 4 or 5 years ago, the NVIDIA architecture suddenly morphed to what's called tensor cores. And this seemed to be a way to deal with the workloads that were coming from TensorFlow and maybe from PyTorch and Caffe and Theano. And so what the frameworks did influence some of the direction of the hardware of the industry sort of heavyweight. And so it does seem like within the push-pull, there's some influence by the framework. And so what I wonder is, to what we've been saying about what needs to happen with efficiency and with memory usage, does some of the responsibility lie with the frameworks, with TensorFlow, to push hardware design, to push hardware innovation, to say maybe the frameworks need to change, and that is one way that the data scientists and the neural network architects like Jan LeCun affect what everyone builds, what NVIDIA builds, what SamaNova builds, what GraphCore builds, what Blaze can build. Is the framework an important focus there?
I think, for me, it's less about the frameworks and it's much more about the workloads and what are the problems we are trying to solve with, at the level of sort of the machine learning problem definition. And I think that hardware design historically has been a very benchmark driven business. And I think, well specified benchmarks can often be the thing that spurns a bunch of innovation. One of the things that I'm most excited about over the last few years is the ML Commons and the ML Perf kind of suite of benchmarks that has come out. It started with training, and now there's inference, and there's data center, and there's HPC, and there's edge, and so on. There's a growing suite of benchmarks, but these represent, at their core, different tasks that we might want to go solve with machine learning. And there's things like computer vision systems and ResNet 50 for object classification. That's probably the one column in that benchmark that has been beaten to death by every single hardware vendor out there on the planet, right? And lo and behold, NVIDIA is pretty good at winning on that column. But if you look at the benchmark kind of across the other tasks, things like recommendation systems, which I know Samanova has done an amazing job at moving the needle on, and other types of tasks beyond computer vision, you start to see a couple of interesting properties. One, no single hardware provider is dominant across every single one of those benchmarks today, because to Val's point, there's this triangle of do you want to be performant or do you want to be general purpose? And if you're going to win a particular benchmark, you're probably going to end up losing some of the other ones.
This is the no free lunch.
Exactly.
Carlo?
I'm excited to see the rest of those columns fill out.
Sorry, Evan, please finish.
I was just saying, I'm excited to see the rest of those columns fill out, and I'm excited to see new workloads get added to these kind of standardized performance benchmarks that everybody agrees on, so that we give the hardware vendors something to focus on as they're building their next innovations.
No, I was totally again agreeing with Evan. It is a great spur. We also participated to MLPerf. However, I believe most of the time that is a drive to software optimization. Mm-hmm. There is still a distinction of what the hardware ultimately support efficiently. That's what eventually, after you finish all the software work, which is crucial, eventually is still making a difference in my view. And that's what hopefully will give us a platform to build for the next steps, for the models that are not there yet.
The next steps being
different types, different models, different type of compute.
Right.
Again, we will start from a place where, every time we do research on models that are not there available, the first thing is that we need to build our custom ops, because the framework doesn't support computation that is not there yet. So that's a normal process. But then the discovery aspect. But then eventually the hardware need to be efficient at that type of computation, in my view.
Raghu, did you want to add anything to that?
Yeah, I think just one additional thing to add, which is, I completely agree with the points made by Evan and Carlo. One additional thing is, you mentioned, the role of frameworks, importance of frameworks.
Yep.
One thing that frameworks do, I don't know if it's a necessary drive for innovation, but one thing it does do is it standardizes the vocabulary.
Right.
If people use the same vernacular to describe certain things, mm-hmm. The certain thing, they keep getting used over and over again. So it gives a framework to reason about, okay, this is what I would want to optimize for. So it does tend to influence hardware design, or at least the vocabulary with which people think. But I think the other thing it does, just speaking of standardization, and since we talked about benchmarks and MLPerf and so on, now whether MLPerf in its current form is the be all end all, what is the sway in the quality of the benchmarks towards one vendor versus the other? That's always going to be there. But I think one thing that it did help the community, in my opinion, is sure, benchmarks are one thing, but it standardized the methodology of evaluation. Because if without benchmarks, you can measure whatever you want and write blog posts and all that. But and if most of the time spent for a particular benchmark from vendor X was in doing the operation, but the pre-processing to get to massage the data in exactly the right way took most of the time, then that would be an unfair comparison. So I think one of the virtues of benchmarks is standardizing the process.
And people can
something that helps keep people honest.
Yeah, people can see where the bottlenecks are for different operations. Although, as everyone's basically saying here, I think we're bumping up against what is measured currently, which might be matrix multiplies, and what we need to do, which needs to be handling the whole compute problem and the dependencies that arise in it, so that we're doing things efficiently with memory, efficiently with bandwidth. Is it fair to say, as our remaining time together dwindles, is it fair to say that we think there will be lots more graph-based workloads that are going to be pressing on compute in the years to come, do we think?
I believe so. It's a direction. It's broadening up the scope of computation, because, of course, it was mentioned by other people already. Graph neural networks, as a family of models, include the models. Every models have been done up to now. Convolutional networks are just graph neural networks for grids, and transformers are just graph neural networks for fully connected graphs. So those the broader scope of graph neural network, to me, it's really a great drive to establish further innovation and further new breakthrough.
Val?
And concur completely. And I think at the edge, some anecdotal examples kind of make that really clear. If you think about a harried mother with 2 children on each arm, struggling through the mall to get to the food court to feed their crying child, or if you think about the grandma with 2 kids on each arm going into the toy store, you have a very different perspective on the relationships between the same objects fundamentally being detected, and yet understanding the relationships makes all the difference, right? And we're really not there yet, certainly not at the edge.
I think we're just about out of time. I want to thank you all so much for participating and for opening up these questions for us. And I look forward to, hopefully we can do this again in a year's time and look back and see what has changed then. So for all of the panelists and attendees, thank you so much, and hope you enjoyed the session.
Thank you all.
Thanks a lot.
Thank you.